Welcome to section 4.5, Parametric Equations. At the end of this section, you should be able to answer these questions. What is a parametric function? What is a parameter? What sort of graphs can we create combining trigonometric functions and parametric functions? What are reasonable t-values for our images? How can we determine parametric equations from graphs? How can we restrict our images? What does it mean to eliminate the parameter? What techniques can we use to eliminate the parameter? First of all, let's define what a parametric function is. If we have two related variables, x and y, and they both depend on a third independent variable, t, the pair of equations in x and t and y and t is called a parametric function. For example, if an object or person is moving up and down vertically while simultaneously moving left and right horizontally, we can use a pair of equations to model the motion. These equations are called parametric equations. This example of a Ferris wheel shows how a person can be moving up and down and left and right at the same time. The independent variable t is called the parameter. Because x and y are often functions of time, the variable t is usually used for the parameter. Before we dive into a discussion and some examples of parametric equations, let's set up our calculator. First, we'll go into mode, and for right now, let's go into degree mode, and make sure we're also in parametric mode. Now let's set our window. We're going to be using some trigonometric functions. So for our t values, we want to make sure that we incorporate all the possible values of a trigonometric function. So we're going to go from 0 to 360 degrees. And we'll use a t-step of 5 degrees. That will allow us to get a smooth curve without taking too long to generate any information. For our x-min, x-max, and y-min and y-max, right now, let's use a window of negative 10 by 10 for both x and y with a scale of 1. And let's clear out. Here's a little trick. I'm going to go into the zoom menu and choose option 5, z square or zoom square. And what that does is gives me equal scales on the x and y axis so that when I graph things, they will appear in the correct proportions. Now let's go back to our parametric screen, entry screen, and I'm going to enter a pair of trigonometric equations. Let x be equal to cosine t and y be equal to sine t. And then I'm going to look at my graph. And right there in the center we can see that we've generated a circle whose radius is 1 that started its graph on the positive horizontal x-axis, went up, over, down, and returned to its original starting position. Let's play with this graph a little bit. I'm going to insert a coefficient in front of my two equations. Let's try 3 for both. Second, insert 3. And when I look at my graph now, I can see that my circle has expanded, so now that it has a radius of 3. Let's play some more. Let's change only one of the coefficients. I'm going to change the 3 sine t to 7 sine t. What do you think is going to happen? Now I have an ellipse whose horizontal semi-axis is 3 and whose vertical semi-axis is 7. Interesting. Let's play some more. I've changed the amplitude of each of these trig functions so that they travel that distance away from the origin, either horizontally or vertically. What would happen if I added a constant or subtracted a constant from the two equations? Aha! My ellipse is now shifted 3 units to the right and 4 units down. Notice how in these equations the translations both reflect exactly what happens to the image. We add 3 to the x information and the image shifts 3 units to the right. I take away 4 units from the y information and the graph drops 4 units. Here it is again. Based on our experiences, we should now be able to come up with equations or an equation for any form of ellipse using parametric functions. Hopefully this is what you came up with. The parametric equations for an ellipse are x equals h plus a cosine t and y equals k plus b sine t, where a and b are called the x and the y radii respectively, and h and k are the coordinates of the center. And we saw that if a equals b, we end up with a circle. Now let's have some more fun with our ellipse. I'm going to go back into my parametric equation screen, and I'm going to take away the translations so that our ellipse is again centered at the origin. Take a quick look at the graph, and here we are. Now this is fine. I can draw a full ellipse by using all the t values from 0 to 360 degrees. But what if I only wanted to draw half an ellipse? Well, we have 2 ways to do that. First, we can go into our window where our t values go from 0 to 360 degrees. I'm going to restrict the t values now to between 0 and 180 degrees. What do you think that's going to do to our image? Let's take a look. We only see the first half of the image being drawn. Do you understand why? Here we've only used the values for t between 0 and 180 degrees, so we only graph half of our cosine or horizontal motion from a maximum to a minimum, and we only draw half of our sine function, going from the middle of the sine function up to a maximum, and then back down to the middle of the vertical information. So that's one way to restrict our window or our image. If I go back and replace the t maximum with its full value, we can also restrict our image by using the Boolean variables that we learned about earlier in the course. I can take either one of these equations and restrict my t values. So I divide by the restriction that t is going to be between 0 and 180. So 0, second test, less than or equal to, option 6, t, then second test logic and t, second test, less than or equal to, option 6 again, 180 degrees. So again, if I look at my graph, I only get half the graph because I'm only using t values between 0 and 180 degrees.